Alright, hello everyone. I hope you guys are doing great. So today we'll be discussing the solutions to Codeforces round 841. So this is a Division 2 round which finished around half an hour ago. And before we begin, I would just like to say that today is a very emotional day for me. And the reason is that I'll finally be becoming a master today on Codeforces thanks to this awesome round. Kudos to the people there at IIT Indore who made this round possible. And yeah, so it's a very emotional day for me. If you look at my profile, you'll realize that I became a candidate master for the first time in Goodbye 2021 contest, which was held on December 29th, 2021. And today, after exactly 1 year, that is December 28th, 2022, I'll be getting my next promotion. So it's been a journey, it's been a roller coaster ride of a journey. It definitely was one, sure as hell was. And I would just like to take this opportunity to say that if you're someone who's struggling right now and you're someone who's not getting results, I would just advise you to stick around more often, and stick to a more journey based approach rather than an outcome based approach. And that is something which surely helps. It definitely helped me, right? As you can see from my profile, you'll realize that my journey was not very smooth. So you can see I've been going up and down from expert to candidate master, so on and so forth. You can see that happened a lot with me. So yeah, that is a part of the journey. I would advise you to embrace the journey and focus on a journey based approach rather than an outcome based approach, right? Anyways, enough with the rant. Let's start with the solutions. We'll be discussing the solutions to the first 5 problems. So let's start with problem A. Okay, so in this problem, basically, we need to maximize the sum of all the elements of an array which is provided to us, and we can do some operation any number of times that we want. And the definition of the operation is as follows. So we'll take two indices I and j, and then we'll take two integers x and y such that the product of x and y is equal to the product of ai and aj, and then we'll replace ai by x and aj by y. So this operation can be done any number of times, and our final goal is to maximize the sum of all the elements of the array. And for some weird reason, we need to output the answer multiplied by 2022. And also another constraint provided to us is that the product of all the elements of the array doesn't exceed 10 raised to the power 12. So this line itself is a hint to the solution to this problem. Like, why will they even give the product of all the elements? Why will they bound the product of all the elements, right? So it turns out that the solution has a term which contains the product of all the elements, and that's the reason. So let's see why that is the case. So problem A, this is a pretty straightforward problem, I would say. So let's first see what happens when we take two indices I and j, right? So we have ai and aj, right? So what we can do is, our final goal is to have two numbers x and y and maximize the sum of x and y, right? So we need to find an optimal value of x and y such that x plus y is maximum and x into y is equal to ai into aj, right? Now how will we do that? So we need x and y such that x into y is equal to ai times aj and x plus y is maximum. I mean, doing this is a good starting point, right? Since we need to maximize the sum of all the elements. It turns out that the optimal value of x and y is nothing but x equals to 1 and y is equals to ai times aj. As you can look at the constraints of the problem, it is allowed to take 1 as one of the factors. So we can take the value of x to be 1. And the reason that this will be the optimal thing to do is that if we take any other factors, let's say x prime and y prime, such that they are not 1 and ai into aj respectively, then their sum will definitely be smaller than or equal to ai into aj. The reason being that their product is equal to ai into aj. So the sum of two numbers is definitely going to be smaller than or equal to the product of their two numbers, right? So that is why if we take any x prime and y prime which are not equal to 1 and ai into aj, then their sum is going to be smaller than ai into aj. But in this case, the sum is going to be ai into aj plus 1. So this is the maximum sum that we can get, right? So this is definitely the optimal thing that we need to do. And now the rest is just observing that we can do this for all the indices. So the optimal order of operations that we need to do is 1 2, then 1 3, so on up till 1n. In this way, the final result will look something like all the numbers from, sorry, this should be, this is not right. Basically, what we'll be doing is, first we'll be doing 1 and 2, then a1 will become 1 and a2 will become a1 into a2, right? Now, the next goal is to maximize it further. So after 1, 2, we'll be doing 2, 3, right? And so on and so forth. So finally, our array will become 1, 1, 1 and product of all elements. So this will be the final array, right? If we keep doing this like this. So the final answer is going to be product plus n minus 1, because there are n minus 1 ones, and the final element is the product of all elements. So that's the solution to this problem. The code again is pretty intuitive. You just calculate the product of all the elements and you add n minus 1 to it, and for some reason you have to multiply it with 2022. So that's your answer, right? Okay, cool. So this completes the solution to problem A. Let's move on to problem B now. Okay, so I'll simplify the problem statement for you here. So we are given an n cross n grid in this problem, and as always we can move from a point ij either down or right. So we can move to ij plus 1 or I plus 1j. Now our target is to start from 1 comma 1 and reach the cell n comma n. And another interesting thing is that in this grid, the number which is written at cell number ij is nothing but I into j. Okay, and what we need to do is we need to maximize the sum of the numbers in the visited cells that we visit in our journey from 1 comma 1 to n comma n. And one thing to notice here is that n is pretty large, so we can't have a linear solution, right? All right, so we need to figure out some kind of formula to find out the answer to this problem. So let's see how we can solve this. Okay, let's move on. So this is problem B. All right. So let's try to draw the grid and see what's happening here. Let's take a 5 cross 5 grid and write down all the numbers. The observation at the end will be pretty intuitive since it is just a Div-2 B problem. Cool. So let's fill all the rows. 2, 4, 6, 8, 10, 3, 6, 9, 12, 15, 4, 8, 12, 16, 20, and 5, 10, 15, 20, 25. So I've just made a grid in which the cell number I comma j is nothing but I into j. Now our path will look like this. So we'll start from 1 comma 1 and we'll go to n comma n. Now one thing to observe here is that when we go to the right or we go downwards, what we can do is we can just greedily take the maximum number that we are getting, and it will actually give us the optimal answer. The reason being that if you look at this path, so we alternatively go right and down, then right and down, and right and down. Then at each step we are basically taking the maximum possible number that we can take, and that is obviously going to give us the best possible answer, right? Since we need to maximize the sum of all the numbers. So yeah, this is the only observation that needed to be made in this problem, and this way we can solve it. So now let's try to come up with a formula, right? We know that our path is going to look somewhat like this. So we'll add first 1 plus 2 in the first row. Then in the second row we'll be adding 4 plus 6. Then in the third row we'll be adding 9 plus 12, so on and so forth. In the last row we'll simply be adding n square, right? And even before the last row, as you can see, in the last row we are adding 25, which is n square. And in the last row we'll be adding some other number. Let's try to figure out a general term for the number which we are adding for all the rows less than n. For the last row we know that it's going to be n square, but for all the other rows it is a sum of two terms, right? So the first term that you can clearly see is that in the first row it's 1, in the second row it's 4, in the third row it's 9, so it's definitely going to be I square, right? For the ith row it's going to be I square. And another thing that you can see is that the next term is going to be nothing, since we are in the ith row and the next term is the next element in that row. It's going to be the previous element plus I, right? So the next term it's going to be I square plus I, right? So this is what we need to add. So this summation for the first n minus 1 rows, and this summation n square for the last row, right? Cool. So now how do we do this? If we further simplify this, for the ith row, what we have is we have I square plus I, which is nothing but 2I square plus I. So we have this summation of 2I square plus I for I from 1 to n minus 1, and finally we have n square. So let's separate this n square for now. We can add this separately and try to focus on this term, right? So since this is a linear summation, we can write it as separately 2 into 1 square plus 2 square, 1 square plus 2 square plus up till n minus 1 square. And the last term and the second term can be separated as 1 plus 2 plus 3 plus up till n minus 1, right? Okay, cool. So let's call this term T1 and let's call this term T2 for now, right? Now our plan is to find out T1 and T2, okay? So what is T1? Well, it is a pretty standard summation. It's very commonly taught to students in high school. So the summation of I square for I from 1 to n is nothing but n into n plus 1 into 2n plus 1 upon 6. So there is a proof of this using binomial theorem, but I won't go there. So this is a pretty standard thing which you should be knowing, right? And the sum for I is again very common. It can be found using a sum of an arithmetic progression. It's nothing but n into n plus 1 upon 2. So we will just substitute n equal to n minus 1 in these two terms, and we'll be able to find T1 and T2, and thus the problem is solved, right? So yeah, this is the solution to this problem. Let's just have a quick look at the code. So I just made two functions. One is for square sum and one is for linear sum. So square sum of n returns n into n plus 1 into 2n plus 1 by 6. An important thing to note here is that since we are dealing everything modulo 1e9 plus 7, we should use modular inverse of 6 in order to divide by 6, and same goes for 2. So linear sum returns n into n plus 1 upon 2. And our final answer looks something like this. First we add 2 into square sum of n minus 1, then we add to it linear sum of n minus 1, and then we just add to it n square, which is the element in the last row. And then we multiply it by 2022 and output, and we are done, right? So this completes the solution to problem B. All right, cool. Let's move to the next problem. And system testing is finished, so it makes sense to just have a look at our rank. All right, so my ranks remained exactly the same, so there were incidentally no FSTs, so that's a good thing. Anyways, let's move to problem C now. Cool. So in this problem, what we have to find is we are given an array, and our goal is to find the number of subarrays such that the bitwise XOR of the subarray has an even number of divisors. That's the simplistic problem statement, okay? So given an array, find the number of subarrays such that the XOR of the subarray has an even number of divisors, right? Okay. Cool. So there is a pretty funny story about this problem. The number of divisors of any number is even if it is not a perfect square, and it is odd if it is a perfect square. And I was preparing for my placement interviews when I stumbled upon a problem on a website called as brainsteller.com. It is a website in which people practice for interviews, right? And there is a pretty similar problem there. So from there, I was quickly able to connect these two properties here, and I was able to realize that this is the property that is going to be used. So that is why I was able to solve this problem quickly. Anyways, so let's write down the fact. So here's the fact. Any number has an even number of divisors if it is not a perfect square and an odd number of divisors otherwise. Now on what basis am I saying this? Well, the proof again is pretty simple, right? So let's see how we can prove this. So for any number, if we try to find out all of its divisors, the divisors will occur in pairs, right? So if x is a divisor of n, then n over x is also a divisor of n, right? we know that n is equal to nothing but x multiplied by n over x, right? So these are the two factors which we are talking about right now. For any factor x, there is a complementary factor n over x, and this happens for every number, but there is one case where x is equal to n over x, and that means that n is nothing but x square. So in this case, we won't be getting a pair. In this case, we'll be getting a single number, and all the other factors will form a pair. So that is the proof. So the proof is similar. The proof is simple. So for any perfect square, all factors, so all the factors other than the square root of that number will occur in pairs. So all factors other than the square root will occur in pairs, but the square root will occur alone, and that is why the number of factors becomes odd other than even. But for numbers which are not perfect square, their square root doesn't exist, so for them the number of factors will be even, and the number of factors for a perfect square will be odd. So I hope this is clear to everyone. I am again repeating that a perfect square will have an odd number of factors because all the factors other than its square root will occur in pairs of x and n over x, but for the square root, x will be equal to n over x, so we will get just one number in that pair, and that is the reason the perfect square has an odd number of factors. Cool. So now it is pretty simple. What we need to do is we need to find, so what we'll do is we'll find the number of subarrays which are odd, and then we'll subtract that number from the total number of subarrays. So we find the number of subarrays with XOR as odd, and then subtract them from n into n plus 1 upon 2. So there are n into n plus 1 upon 2 total number of subarrays. So we'll, from this number, we'll be subtracting the total number of subarrays which are odd, whose XOR is odd. And by XOR is odd, I mean XOR is perfect square. Right? Okay. Now, how do we proceed now? Well, the problem is now very much simple. So what we have to realize is that for any subarray from L to R, so for L to R, if we have calculated the prefix XORs, right, then the XOR of L to R, so XOR of L to R is nothing but prefix XOR of R and XORed with prefix XOR of L minus 1. This is a very well known property, and I won't be proving it because it's pretty obvious, because the XOR of the first L minus 1 terms will be cancelled out from this first term, and so we'll be left with the XOR of terms from L to R, right? So if we are looking at some perfect square, let's say we have a perfect square y. So we have a perfect square y, and we are at an index I. So we are at index I, and we need to find out the total number of subarrays which has a XOR equal to y. So that will be nothing but the total number of subarrays. So total number of subarrays with XOR equal to y is equal to number of j less than equal to I, such that prefix XOR of j minus 1 is nothing but y XOR prefix XOR of I. This is pretty obvious from what I have written above, because if we want y to be prefix XOR of R XORed with prefix XOR of L minus 1, so we want y to be p XOR of R, R is I here, XOR p XOR of j minus 1. So p XOR of j minus 1 would be nothing but p XOR of I XORed with y, right? So that is what I have written here. So we need the count of the number of indices such that their XOR is this number, and this can be maintained. So we can just simply maintain a map or something. A map might give us TLE, so it's better to just keep a vector instead of a map, right? And yeah, the thing to note is that the number of perfect squares is of the order square root of n, and so we only need to maintain a map of square root of n numbers, and so the final time complexity becomes O of n into square root of n, right? I hope this makes sense. Let's just have a look at the code. That will make much more sense. So first what I'm doing is I'm computing all the perfect squares. So n up to 600 is enough, so we only need to consider the first 600 squares, because 600 square is 3.6 into 10 to the power 5, which is more than enough, right? And I'm maintaining a vector which has the XORs, which is the count of all the XORs, all the prefix XORs, right? So when I'm at an index I iterate over all the perfect square and find out the count of x XORed with my prefix XOR, and yeah, I keep doing it, and finally I subtract the answer from n into n plus 1 upon 2. Okay. Alright, so this completes the solution to problem C. Let's now move to problem D, which in my opinion is much easier than even problem C, right? Cool. Alright, so in this problem what we have is we are provided with an n cross m grid. The sum of n into m is less than 1e6 over all test cases. And what we need to do is we need to find the largest value of L such that there exists an L cross L square inside the grid, and the value at each cell in that square is at least L. Okay, that's the problem. So you need to find the maximum value of L such that there exists an L cross L square inside the grid, and the value of all the cells inside that L cross L square is greater than or equal to L. Okay, cool. I won't spend a lot of time in this problem, mainly because the solution is very intuitive if you know just what to do. Okay. Alright, so the solution is pretty simple. It's even enough for me to mention just one word, and that word is binary search for answer. So this phrase is enough for you to solve the problem, right? So what we'll do is we'll simply apply binary search for answer. Okay. So what is the answer here? So the answer here is L, right? So we'll apply binary search over L. Okay. Now, to apply binary search, what we need is we need a checker function. Okay. So we need check of L. So check of L will return true if there exists an L cross L grid such that all elements in that grid are greater than or equal to L. Because if this is true, then that means that a particular value of L can be the answer, otherwise a particular value of L can't be the answer, right? Another thing is that we can apply binary search here. The reason being that if there is an L cross L grid, so I'll just write that down. If there is an L cross L grid such that all elements in that grid are greater than or equal to L, then there is also an L minus 1 cross L minus 1 grid such that all the elements are greater than or equal to L minus 1, right? So L minus 1 cross L minus 1 grid such that all elements in it are greater than or equal to L minus 1. We can just take any L minus 1 cross L minus 1 subgrid from the L cross L grid that we have, and that will satisfy the condition, right? And that is the reason that if the answer is true for some L, then it is true for all values less than equal to L as well. So this checker function will return true if there is an L cross L grid such that all the elements in this grid are greater than or equal to L. Otherwise it will return false. Now our only job is to implement this checker function. How do we do that? So we iterate on all cells ij, and look at the subgrid. So we'll look at this. We'll look at the L cross L square, which is starting from this point I comma j. So we'll look at the subgrid from I comma j as its top left corner to I plus L minus 1 and j plus L minus 1 as its bottom right corner, right? And all we need to do now is to figure out the number of cells which are greater than or equal to L. And it turns out that we can do that pretty easily. So what we'll do is we'll create an auxiliary array, and all the elements of that auxiliary array will be 1 if ai, so bij. So we'll create an auxiliary array. So create an auxiliary array B such that bij is equal to 1 if and only if aij is greater than or equal to L, right? So once we create this B array, in our original array, we want to find the count of the number of elements which are greater than or equal to L. But in B, we want to find the number of elements in this subgrid. So in this subgrid, we want to find the number of elements which are greater than or equal to 1. So in the array B, we are talking about the number of elements which are 1, right? So all we need is, we need the sum of elements in B, right? So the sum of elements in a subgrid can be very easily computed using 2D prefix sums. Using 2D prefix sums. It is a very common technique. I think you guys must be knowing about it, but if you don't, then you can check that out from any Codeforces blog. It's a pretty well-known technique. So you can use 2D prefix sums and you can compute the sum of all the elements of a 2D array in constant time. Okay. So yeah, we'll just iterate over all the starting cells, look at the L cross L subgrid starting from that cell and find out their prefix sum in the array B. If it is equal to L square, then that means that all the elements are greater than or equal to L, right? And we are done. So this is how we implement the checker function, and the rest is you simply apply binary search. So that's the solution. Let's just have a look at the code. Okay, so the code is pretty simple. So this is the standard binary search that we are talking about. So I'm straight away building my prefix sums. So this is a standard technique to build the prefix sums, and then we iterate over all the starting cells and we check if there is a cell which has the prefix sum equal to L square. And if that's the case, then we say that L is equal to mid, otherwise we say R is equal to mid. This is what we do in binary search, right? So yeah, this is how we solve problem D. I hope it's clear to everyone. Cool. So now let's go to the last problem, problem E. And again, I'll admit that this time the problem E was definitely a bit on the easier side as compared to a normal problem E. Reason being that, at least for me, it was the case because I have already solved a lot of problems which is similar to this problem. Like the core idea is similar to the core idea of this problem. So yeah, that's the thing. Cool. So let's try to read this problem. So we are initially given an undirected graph with n nodes. So we have a graph with n nodes and initially there are no edges. And the nodes are numbered obviously from 1 to n. Okay. Now what we want to do is we want to add m edges to this graph, and we want to add these edges so that the graph won't contain obviously any self loops or any multiple edges. Okay. All right. Now another interesting property that this graph must satisfy is that if there is an edge connecting two nodes u and v, then the weight of that edge must be equal to the GCD of u and v. Okay. Cool. Now we are allowed to perform an operation to add edges, and the operation looks like this. So we'll perform this operation as many times as we want. So we'll choose any integer k greater than or equal to 1, and then we'll add exactly k edges to this graph, and each of these edges will be having a weight of k plus 1, and these k edges and the cost of adding these k edges will be equal to k plus 1. Now since the weight of the edges that we are adding is k plus 1, a thing to note is that there should be pairs whose GCD is equal to k plus 1 and they don't yet have an edge between them. And if that is the case, then we'll choose such a pair and we'll add an edge because of this condition which is given to us, that any edge between u and v should have a weight equal to GCD of u comma v. Okay. Cool. So yeah, this is what they have told here, which is what I told you. Right, so now we are given n and m, and we need to find out the minimal cost of forming a graph with n vertices and m edges. So the cost of doing an operation with k is equal to k plus 1. Okay. Alright, so let's just write down some preliminary observations. Problem E. Cool. So let's write down an observation. So what happens is that if we do an operation with a value k, its cost is going to be k plus 1, but the number of edges that I'm getting is also equal to k. So the number of edges that we get is equal to k, right? So here's the deal. So if we take a number, k and do an operation, then we'll be getting k edges, and its cost is going to be k plus 1. All right. So let's see whether doing an operation with a small value of k is better for us or doing an operation with a bigger value of k is better for us. Okay. So let's say we have to make 6 edges, right? And let's try to compare what happens when we do an operation with k equals to 6 and when we do an operation with k is equals to 3 twice. So let's say we have m is equal to 6. Now if we do two operations with k is equals to 3, then we will be getting a total cost of 4 plus 4 is equal to 8, right? Cool. On the other hand, if we do one operation with k is equals to 6, if we do one operation with k is equals to 6, total cost will be 6 plus 1 is equals to 7, right? And this is pretty simple. So if we are doing a total of x operations, right? So if we are doing x operations, then cost will be m plus x, right? Because in every operation we are getting an extra cost of 1, right? So what we need to do is we need to minimize the number of operations that we do. And if we want to minimize the number of operations, then it's optimal to take larger and larger values of k, right? So that is why it is always optimal to choose the maximum value of k possible at every instant, right? Now the question is, when is the value of k possible? It's pretty obvious. The value of k is possible if there exists a pair u comma v such that GCD of u comma v is k. So an operation k is possible if there exists a pair u comma v such that edge u comma v does not exist and GCD of u comma v is equal to k, right? So the number of times that we can perform an operation k, so the number of times we can perform operation k is equal to number of pairs. So number of pairs ij less than equal to n such that GCD of ij is equal to k, right? Cool. So this is pretty obvious. So the number of times we can perform an operation of type k is going to be the number of pairs whose GCD is equal to k. So all we need to do is, for all k from 1 to n, find out the number of pairs. So find out the number of pairs with GCD equal to k, and then greedily keep doing operations with the largest possible value of k. So this is the simple solution. The only caveat yet which remains is to find these number of pairs. And it turns out that there exists a pretty standard trick using which we can find out the number of pairs which have a particular GCD for all the elements from 1 to n in a total of O of n log n time. And what we can do is that we'll first calculate the number of pairs which have their GCD as a multiple of k, and then we'll iterate over all the multiples of k and we'll subtract the number of pairs which have a GCD that. Okay, so I'll formalize this. So first find out the number of pairs. So for each I, we'll do this. First find out the number of pairs which have GCD as a multiple of I. And this is nothing but the number of pairs such that both the elements in the pair are divisible by I. So this is going to be nothing but n by I floor multiplied by n by I, right? So sorry, n by I C2. Sorry, yeah. So because there are n by I numbers which are multiples of I, and if we select any two numbers which are multiples of I, then their GCD is going to be a multiple of I as well, right? So this is going to be n by I C2, right? And then for each multiple j of I, So obviously j is greater than or equals to 2i. That means j is not equal to I. So for each multiple of j greater than I, what we'll do is we will subtract answer of j from answer of I. Right. So let's say this is equal to answer of I. Initially we have all the pairs whose GCD is a multiple of I. And from that we are subtracting the number of pairs whose GCD is 2i, then we subtract the number of pairs whose GCD is 3i, then 4i, and so on. Right? And if we do that, we'll be left with only those numbers whose GCD is exactly equal to I, because we are subtracting all the pairs whose GCD is a multiple of I for all multiples from 2i, 3i, 4i, and so on. Right? So this is a very standard trick. There is also a way to find out this thing using a technique called as Mobius inversion, but I won't be going there because I've always found that this trick is very much intuitive and it's much simpler to implement than Mobius inversion. So yeah, this is it, right? So this is the solution. Using this, you can calculate the number of pairs which have GCD equal to I. Let's have a quick look at the code. So the code is pretty intuitive. I iterate in the reverse order from n to 1. And initially I initialize the answer as count C2, where count is equal to n by I. And then I just subtract the answers of all the multiples. And so now f of I will denote the number of pairs which have GCD equal to I. And then what I do is I just iterate in reverse order and greedily take the maximum possible number of pairs that I can take. Finally, if I can take m pairs, if I cannot take m pairs, then the answer will be -1. Otherwise, we have the answer computed, right? Okay, so this completes the solution to problem C. So this is all that I had in mind today. Thank you so much for watching, and I'll see you in the next one.